Sound check, sound check. Hoover High AP Chemistry. This is the answers video for day 56. This was the one given out the Wednesday before Thanksgiving break. And since we're not meeting on Friday, I'm not going to give another assignment out. We'll pick that assignment up the Monday that we return. So let's go ahead and get through this. So there is an instruction video that you should watch before this. And some of the answers, many of the answers to that are simply in that video. So question number 1 is name the 5 types of reactions and give an example of each. So that's in the instruction video, the first few minutes of that. So go ahead and do that on your own. That's a pretty straightforward question. Now the rest of this assignment is going to require a variety of different sheets. So let's go over those, what you should have available, either pulled up on a tab or preferably printed out. So right here is a table called the activity series, and we'll talk about what that is. You should have that out and available. This comes straight from your textbook. You can open to the appropriate page and find that table in your textbook. Next, there's 2 sheets that relate to charges, ionic charges. One of them is this charge numbered by ions. It's a periodic table which shows the charge that any of the elements on the periodic table will take on. Some of them are more than one element, so we did this back in the foundations unit. The other one that goes along with that is the 60 common ions. What the periodic table that you just saw has is every single element on the periodic table. What it doesn't have that this has is down here in set 3, some of these polyatomic ions, I like to call them covalently bonded ions because they are covalent bonds. So like PO3 phosphite, PO4 phosphate. So those would not be on a periodic table because they're compounds. But it shows you the charges of these, and you do come across these quite a bit. You really effectively treat these as elements. They don't come apart in solution. They just transfer from one side of the reaction to the other. Okay, the next thing you should have is this, solubility rules for water. And it's for water only. It's not any liquid that you decide to put these things in, but it's for water. So have that available. Of course, you should always have available a regular periodic table. This is just the standard one that we've been using in the course. And also you can pull up in the reference sheets. This is kind of a condensed sheet, couple of sheets on a net ionic equation, how to write a net ionic equation. So what I do in the video is taken from this, but I recommend you watch the video and listen to the explanation once, and then you can use this if you understand it. Okay, so let's go ahead and get started. So you've written the 5 types of reactions. The next set of exercises is use the activity series reference sheet to determine which of the following would take place. So these are single replacement reactions. It's one of the types of reactions up there, and you should again watch the instructions video because it explains how to do this and explains why this happens. But just to take a simple example, calcium is a pure element, so it has no charge to it. It has a full set of electrons. Zinc and chlorine. Zinc is a 2+ element. It means if it gives up electrons, it wants to give up 2 electrons. Chlorine is highly electronegative, so it takes in electrons, and each chlorine takes in 1 electron. So this gives up 2, so it becomes a 2+ charge. Each chlorine takes in 1, but since this is giving off 2 and you need enough chlorines to catch those 2 electrons, then you need 2 chlorines. So that's why the 2 subscript down there. So it's 2 times -1 will give you 2 chlorines, okay? Now calcium, when it ionizes, is also a 2+. So it has that in common with zinc. What happens here is the calcium gives 2 electrons over to zinc. And what that does is it makes zinc over on the product side neutral. It no longer is 2+. In order for zinc to bond with chlorine, they have to be charged. The chlorine has to have a negative, and the zinc has to have an equal and opposite positive. If the zinc suddenly becomes neutral, it has no charge to it because it picked up 2 electrons, and so it's now a 0, it's no longer going to bond with chlorine. Where those 2 electrons came from was calcium. Calcium gave 2 electrons over to zinc, made it neutral, but then that made calcium, its natural ionized state is 2+, just as zinc. So it's now going to come over here and it's going to bond with the chlorine, just the same way zinc did over here. 2+, 1-, and then there's 2 times the 1-. So the question about this is, will calcium give 2 electrons to zinc to cause this reaction to happen? Or will the opposite occur down here? Here you notice it's exactly the same reaction here, but the zinc is the lone element, the calcium is bonded, and then they switch places. Again, that's why it's called single replacement reaction, where the calcium comes out, it has a 0 charge, and the zinc would have a 2+. It doesn't seem likely that both of those reactions would take place, even though logically, based on the way I explained that, this one's just as likely as this one. So how do you determine whether this reaction will take place, calcium takes the place of zinc, or this one, zinc takes the place of calcium? And that's where the activity series comes in. So the rule is very simple. The rule simply says that if the lone element, in this case calcium, or in this case zinc, the lone element is above the other element, the element that's in the bond here, then the reaction will take place. If it's below the element that's in the bond here, then the reaction will not take place. So let's look at these two and see which one will take place. So we find calcium, and calcium is up here. It's the 4th one down from the top. Zinc is down here, it's 9th down from the top. So since calcium in this first reaction is the lone element, it will pass 2 electrons over to zinc and cause this reaction to take place. So that will take place. So calcium above zinc means the reaction will take place because calcium's the lone element. In this reaction, zinc is the lone element. So will it replace calcium? Well, again, the same two. You look right here, zinc is below calcium on the table here. Therefore, the reaction will not take place. If the lone element is below the element that's in the compound initially, then that reaction will not take place. The way I think of it is electrons fall down the activity series. So this reaction where calcium passes 2 electrons over to zinc, that's this first reaction, will happen. But in this case, for it to happen, zinc would have to pass 2 electrons up to calcium. In this direction, that will not happen. Electrons don't travel uphill on the activity series, they fall down. They fall down the activity series. Okay, so that's how you use the activity series. It's very simple. So this one, determine whether it would take place. It's just a simple yes or no. But I want you to write out the reason just briefly, just to reinforce the concept. So calcium is above zinc. Go ahead and just write out that short sentence to reinforce why it is. Okay, this one is no. This reaction will not take place because zinc is below calcium. Okay. All right, let's do some others here. So here the two elements in question are potassium and Ag, silver. So we come over here, and potassium's way up here. It's second. So it's the lone element. Okay, it's the lone element right there. So there it is, and silver is way down here at the bottom. So the electrons are going to fall from the lone element to the ion down here to silver. So electrons fall down, so potassium is above silver on the activity series, so this reaction will happen. Okay, these two, nickel and magnesium, so you just find them. Here's magnesium up here, and the lone element, by the way, in this reaction is nickel. Here's magnesium up here, here's nickel down here. So nickel, being the lone element, would have to pass the electrons, and it's not going to pass them uphill. So no, that reaction will not happen. Nickel is below magnesium. Okay, and tin is Sn and Ba is barium. So SN is the lone element. That means it's the one that has to be above. You can just remember, the first one has to be above the second one. That's kind of a quick way to remember it. Okay, so barium's way up here, and tin is way down here. So tin is not above barium. Tin is below barium, so that's a no. All right, let's do a few more, and I'll leave a couple for you to do by yourself. Right here we have Mn is manganese, and Pb is lead. So we come down here, and here's manganese right here, about the 8th element down, and lead is down here. So manganese is above lead, so manganese is above lead, so that will take place. This will pass its electrons over to lead, okay? So yes. Okay, lithium, and that's aluminum. That's an Al, aluminum. Lithium and aluminum. Lithium's actually number one, so nobody beats lithium as far as being able to pass electrons. And aluminum, excuse me, aluminum is, where's aluminum? There it is. Okay, it's about the 7th one down. So yes, lithium being the lone element will pass its electrons over to, lithium will pass to aluminum. So lithium's above aluminum, so that will take place. Again, the first one has to be above this one. Okay, and I'll do one more with you here. This is chromium, and gold is Ag. Gold is absolutely at the bottom right there. Chromium is right here, kind of in the middle. So chromium is above gold. So chromium is above gold. That's where it needs to be. The first one has to be above the second one. So yes, that will take place. Okay, you do the last two on your own. Okay, it's a pretty easy concept. And that's what the activity series tells us about a single replacement reaction. Okay, let's move over to solubility rules. So you're going to need this sheet. So let's look at this sheet and what it's kind of telling us here. And it's, you know, is it a complete sheet? No. So let me say a couple of things about this. There are some sheets that have more of these. This is one I got from a online University of Kentucky course, so it's one that they use at the university level. It's pretty much as complete as you need it to be. The other thing is, insoluble means it won't dissolve in water. Soluble means it will dissolve in water. The fact is, as we're going to learn in a short time in the future, you know, very few elements are totally insoluble. They might just very slight little bits of them dissolve off in water. For example, here it says that carbonate is insoluble in water. Yet, if you put carbonate in water, little trace amounts of carbonate will come off in the water. So to say it's 100% soluble or 100% insoluble, as I say, we'll learn that later, something called the solubility product, and we'll learn about that later. Okay, so let's see what this is telling us. It's telling us everything in this column is soluble. These guys are 100% soluble. They'll dissolve with anything they're with. The moment you see any of these, bam, it's going to dissolve. These are pretty much 100%, but not quite. These will dissolve with anything they're with except these three. So if you have gold chloride or mercury chloride or lead chloride, or again, any of these combinations here, these anions and cations, those will not be soluble. So these are soluble except when any of these are paired with any of these. Okay. Down here, sulfate, same thing. It's soluble with pretty much anything except these 5 ions, these 5 cations. With those, it will not be soluble. Okay, insoluble. Everything down here is insoluble with this exception, these 4 right here. I'm not sure why they didn't list everything over here, because everything over here should be soluble. But you see they listed some of those. They listed the first 4 there, over there. Okay, maybe it's because these are just pure L. Well, that's not a pure L. I don't know. I don't know why they didn't list everything over here. But pretty much everything over here is insoluble except these. So OH, that's hydroxide, is insoluble except when it's with Ca, strontium, or barium. So like calcium hydroxide would be soluble. That's insoluble except when it's with one of these. So with one of these, this would be soluble. Same with the sulfide ion. Okay, so that's insoluble with anything except these 3. And down here, these are insoluble all the time. But the question comes up: what if one of these is paired with one of these? Who wins? The insoluble guy that never breaks up, or these? The answer is these guys. So potassium would be K2, potassium carbonate would be K2CO3. If you had that and you put that in water, it would become soluble. So again, exceptions, you read this, exceptions for all anions are these. Even these guys down here, this will dissolve. So you just have to kind of practice a little reading this table, and that's what this next exercise is designed to do. So let's go ahead and do that. All right, so let's go down these. These were done in the video, but I'm going to do them here. I want you to do these on your own, okay? So KCl, I'm going to do them all because I want you to know. Try to do them on your own though. Don't just copy. So I want you to know whether you're getting them right. So okay, so first one is KCl. Okay, right there, K dissolves with everything. So is it soluble? Yes. You don't have to write a reason for this. Just write yes. Okay, silver chloride. So we come over here. There's chlorine or chloride. It's soluble with everything except one of the 3 that it's not is AgCl. So that is not soluble. This is soluble except when it's paired up with one of these 3. So that's going to be no. Calcium hydroxide. Okay, hydroxide is not soluble. It's insoluble with everything except these 3 cations. Calcium is one of them. So that is going to be soluble. So this is insoluble except if it's paired up with this and these other 2. So this is going to be soluble when those 2 are together. So again, you're just writing yes, is it soluble, or no, it's not soluble. Okay, strontium sulfate. Strontium sulfate. So sulfate is soluble with everything except these 5 cations, and strontium is one of those. So that means this is insoluble. So no, this is not soluble in water. Silver nitrate. Okay, nitrate is soluble with everything. Calcium sulfide, calcium sulfide. And sulfide is insoluble with everything except one of the things it is soluble with is calcium. So this is yes, this will dissolve in water. Magnesium sulfide. Okay, so there's sulfide. It's insoluble with everything except these 3, but magnesium is not one of those 3, so that will be insoluble. Again, you should be stopping the video. Try to do these first and then watch the answers, okay? No copying. All right, lead chloride. So there's chlorine, and lead it's soluble with everything except lead, so these 2 will be insoluble. Don't be fooled by the 2 there. That doesn't make a difference. Subscripts don't make a difference. It's just what are the elements. So that will be insoluble. Okay, potassium, by now I think we know that's soluble with everything. Okay, barium sulfate. So we come over here and we have sulfate. And there we have barium as one of the exceptions. So sulfate is soluble with everything except these 5. Barium is one of those 5. So these 2 together are insoluble. They will not break up in water. Strontium hydroxide. There's hydroxide. It's insoluble with everything except these 3. And strontium is one of those 3. Strontium hydroxide. So that will be soluble. Okay. Calcium carbonate. So right down here we have carbonate. Calcium is not one of these that'll break up with everything, so that's going to be insoluble. That's eggshells basically. You put eggshells in water, they're not going to dissolve. So what did I say? No, that's insoluble. Sorry. That's insoluble in water. Okay. Mercury, and that should be a small r, not a big R. Mercury bromide. So we come over here. Bromide is soluble with everything except these three, and mercury is one of those three, so that means these two together are insoluble. They will not break up in water. Potassium carbonate, that's the one I mentioned earlier. What if you put one of these that always is always soluble with one that says it's never soluble? The answer is it will be soluble. Potassium will break up with everything. And finally, aluminum phosphate. So phosphate doesn't break up with anything unless it's one of these up here, and aluminum is not up there, so that will be insoluble. That will not break up in water. Okay, there you go. Be sure you're comfortable with those and how to read this chart. You'll have plenty of practice reading this chart at a later time. Okay, so here we go. You're gonna start to feel like a real chemist after this exercise. You're gonna really feel like you know something about chemistry here. And all I'm giving you is the name of two compounds. They're both ionic compounds. And you're asked to write a net ionic equation. And I love these exercises because they kind of tie together everything you've learned in this class so far. And even though they seem long, there's 9 steps to them, you'll catch on to the steps pretty quickly. All right, they're not that hard to do. Okay, so the first thing we got to do is, we want to write the net ionic equation for potassium sulfate and calcium iodide. And this is the exact same one that's in the instruction video. Okay, so if you watch that, try to do this without watching the video, but you always have that video, or you can just watch what I'm going to do here. So what we got to do first of all is put together potassium sulfate. So you look over at your periodic table and you say, there's potassium right there, it's K. So I know that's K. Now sulfate, you look over here, you say, I don't see sulfate. That's because it's not a pure element. It is a compound that forms an ion. So the place you're going to find that is down here in your 60 ions sheet, this third set down here. Okay, and that's where you can learn about some of these polyatomic ions, or what I call covalently bonded ions. And sulfate, you look at it, and here it is. There's sulfate, and there it is, SO4. Don't worry about the charge yet. Just put SO4 down. So it's KSO4. That's going to be the first compound. Now, these are the reactants, so you're going to add that to calcium. That's Ca. You get that off your periodic table. And iodide. Remember, iodide, the second word in a ionic compound, unless it's one of these like sulfates or carbonates, you change the last part of it to IDE. So iodine becomes iodide. It's going to be the anion, the one that takes in the electron, okay? But it's just simply CaI. Okay, so there are your two reactants right there. Now we go to the next step. You create a double replacement reaction. So what you do is take, this is a cation, this is a cation. This is an anion, this is an anion. So these two just swap places. And it doesn't matter which order you put them in, whether you put the new one first. So we're going to put the K with the I and the Ca with the SO4. So I'm going to write that right here. So first of all, I'm going to rewrite this so that I have the entire reaction here. The reactants are this. And the products are after you switch these. So it's going to be CaSO4. And the K moves over and pairs up the I. That's called a double replacement reaction. So there you go. You got your reaction. Okay, now you have to charge balance it. Remember, ionic bonds have to be charge balanced. So what you have to do is go through and identify the charges on each of these elements, or in the case of sulfate, on the sulfate. So you can either do that from your 60 ions, right here. So for example, we have K is just a plus. That means it's a +1 or a 1+. So we'll go ahead and put that here. And SO4. Now you can't find that from the periodic table, but you can find it from the 60 ions. And we just pointed to it earlier. SO4 is a 2-. Okay, then we come to Ca. Now remember, you could do this just from a periodic table. You learned how to do that. Ca, it wants to give up 2 electrons to be like the nearest noble gas, which is argon over here in the row before it. So if it can lose these 2 electrons here, then it will lose its 4th orbital, and it will have a full valence orbital, which will now be its 3rd orbital. Remember how that worked? These over on this side want to lose electrons to be like the nearest noble gas, which for calcium is going to be argon. So this loses 2 electrons. That gives it a 2+ charge. Or you could have done it the easy way and just looked here that calcium is a 2+ charge. Or you could have looked here, just showing you what your options are here. On the periodic table of ionic charges, calcium is a 2+ charge. Okay? Several ways to know that. So that's a 2+. Iodine is a 1-. Or you could have seen it here. It's a 1-. Or you could have come over here and used your reasoning ability and said, if iodine can pick up 1 more electron, it'll be like the nearest noble gas, which is xenon. So it's going to be a 1-, meaning it wants to take on an electron, which is a negative charge. So it's going to have a 1- charge. Any way that you do that, you come up with a 1- here. Okay, and then over on this side, they're not going to change. Calcium is still going to be a 2+. Sulfate is going to be a 2-. Potassium is going to be a 1+. And iodide is going to be a 1-. So you've got charges for everything in this reaction now. Well, let's look at the product side first over here. Everything's balanced. 2+, 2- balances. You don't have to change anything. 1+, 1- balances. You don't have to change anything. Over on this side, though, they're out of balance. So this is a kind of a review of the fundamentals lesson on how to put these together. If I have a 1+ charge for potassium and I have a 2- charge for sulfate, these have to be balanced. So that means I need 2 of these 1+ charges to balance out with that 2-. 2+, 2-. So what I need to do then is I need to have 2 of these potassiums. So what I'm going to do then is put a 2 down there as a subscript, meaning I have 2 of those potassium ions. There's the 2 times 1 will give me 2+, and that matches up with 1 of the 2- sulfate ions. Okay, so that's how that works. Same thing over here. I have 2 calcium, 1 negative iodide. I need 2 of these iodide. Each of these iodides wants to catch an electron, wants to pull in 1. But calcium's going to throw off 2. It's going to give up 2. So that means you need a second iodide in order to catch both of those electrons. So you need 2 iodides. So that's going to go ahead and become this times 2. So that's going to put a subscript of 2 there. Okay? So now everything is charge balanced. 2+, 2-, 2+, 2-, 2+, 2-, 1+, 1-. Okay, each of the compounds is charge balanced. So those are the subscripts that you needed to add. Okay, number 3. Determine the charge number of each element or compound. Oh, I did this here. So I already did that, okay? I wasn't reading carefully. There you were just creating the double replacement reaction. Since I had it already written, it makes sense to just go ahead and finish it. So this is really what goes down. Determine the charge number of each element or compound using 60 common ions, or the others that I just went over. So that really, we did that's step 2, and step 3 is right here, okay? All right, step 4. Adjust the subscripts to balance the charge. Well, we did that too. We adjusted that subscript and that subscript so that the charges are now balanced. So we did a bunch of things all in one spot there, okay? So all of that is already taken care of. Okay, so let's come down here, and without writing all the charge numbers, let's write that equation a second time. Okay, so it's going to be... Okay, so now we have to determine, when you put each of these in water, are they going to dissolve or are they not going to dissolve? Are they going to break apart or not? And that's where we go to the solubility rule sheet again. Okay? So let's look at the first one, K2SO4. Well, by now I think we know K breaks up with anything. Okay, and SO4 breaks up with almost anything down there. So this means when you put it in the water, the moment you splash it in the water, it's going to dissolve. It's going to break apart. So we call that aqueous. So on dry land, K2SO4 can form a compound. You could actually have it in a jar on the shelf in your chemistry lab. But the moment you throw that in water, they're going to break apart. And let me tell you how they're going to break apart. There's no such thing as a K2 molecule. Don't get fooled into that. What these are going to break apart into, I'll just write it over here, is you have two K ions here. So you have, it's going to break into a K1 plus ion. It's going to break into a second K1 plus ion. And then it's going to break into an SO4 ion there. Okay. All right, so you're going to end up with 3 ions coming out of this. This is not K2 like H2 for hydrogen gas or O2 for oxygen gas. It's not a molecule. It's just 2 Ks. Just think of them. They could be stuck onto this SO4 anywhere. They're not even necessarily next to each other. Okay? All right, so that's going to be that one. Now, how about this one? All right, so Ca and iodine. So it says iodine breaks up with everything except these 3 substances, but calcium is not one of those 3, so it is soluble with calcium. So this is also going to be an AQ. Now let me point something out that I pointed out in the instruction video. This will break up in water, this will break up. If either of these were compounds that will not dissolve in water, that would be insoluble in water, you're done with the problem. You can't do any further because you cannot have a chemical reaction over here. These both have to be able to break up in water in order to have the chemical reaction take place, okay? All right, now we come over here and we look at CaSO4, and SO4 is right here, and it's soluble with everything except these 5, and Ca is one of the 5. So CaSO4 is insoluble in water. So what does that make it? That makes it a solid. It basically forms a solid. Usually the solid will sink to the bottom of the beaker or wherever you're doing the chemical reaction, and that's called a precipitate. Okay, I'll write that word up here. This is a solid and it's called a precipitate. All right, so this one is not going to break apart. And then finally the last one, well, of course, K breaks up with everything, so that's aqueous. What it means is, even though it's on the product side of the reaction, you say, well, it's on the product side, so that got put together, right? No. K and I can bond together on dry land, but as long as they're in water, they're going to stay apart from each other. You're going to have a K plus ion and an I minus ion, and they're not going to come together in water. So that's what aqueous means. It means they stay dissolved or separate from each other. Okay, so let's move on down now. Let's write all this down here, and we're going to balance the equation. That's the next step. So this is really bringing in a lot of the skills that you've learned earlier in this class, and that's why I like these problems. Okay, there you go. So I left space to write our coefficients. So this is a pretty easy one. So we have K. I'm going to do it. I'm not going to use the box method. Again, you want to get away from the box method because it could take a half a page to write all the boxes. So learn to just count atoms. So I have K, I have Ca, I have I, and I have SO4. SO4, remember, with these polyatomic ions, these covalently bonded ions, do not come apart in water. You can treat this like a pure element. In fact, if you want to emphasize that, you can put that in parentheses. And you can put that one in parentheses too. So this is going to stay together throughout the entire problem. It's not going to dissolve. It's not going to break apart or rearrange. Okay, so now we count. We have 2 Ks on this side. We have 1 on this side. Calcium, we have 1 and 1. Iodine, we have 2. And over here we have 1. And SO4, we simply have 1 there. If we had more than 1, there would be a coefficient a subscript outside of the parentheses. So there's 1 on this side, 1 on this side. So the only things that are out of balance are iodide and potassium, and you can balance those all in one shot by simply putting a 2 right there. So now you have 2K, so this changes to a 2. And you have 2I, so this changes to a 2. So you have 2, 2, 1, 1, 2, 2, 1, 1. Everything's in balance. So there's your balanced equation. You can put 1s in front of these, but not required. I like to do it because it emphasizes that there's a 2-to-1 relationship between that, or between that, 2 to 1. So it emphasizes there's that kind of relationship. Okay, now you're going to separate all of these ions. So I'm going to warn you, I'm going to sharpen my pencil here. I'm going to warn you. That's why I'm getting a sharp pencil for this. This is going to take the entire width of the page. So you want to start way over here on the left, okay? So we're going to separate all these ions. So remember what we said about the K2. It's not a K2 molecule. It's 2 K1+ ions. So the way you write that is this. 2K, 1+ is the charge, and you should write the state as well, aqueous. Remember the states are solid, liquid, gas, and aqueous. Okay, next we have the sulfate. There's only one of those, so we're just going to write SO4. It's a 2-, and it's aqueous. There's a name for this equation, and if I don't forget, I'll say it before I get to the end of the problem. Okay, now we have, I got to be careful I don't run out of space here. I have 1 Ca, that's a 2+, and that's aqueous. I'm going to write a little bit smaller. And I have 2 of the iodides. 2 of the iodides here. Again, that's not an I2 molecule. Iodine can form a molecule, an I2 molecule, if it's a gas, but this is not a gas. It's in solution. Okay, so that you're going to do that the same way you did the K2. So that's going to be 2I, 1-, and that's aqueous. Now we're ready to go to the other side of the arrow. I'm hoping I don't run out of space. Well, this is going to help us. This does not break up. This is a solid, so that's not ionized. That's going to stay together. That they're going to get put together in water, and they're going to stay together. So that's going to be Ca, SO4. There's no charge on it because the 2+ and the 2- are balancing each other. So you don't put a charge above something that does not ionize. That's solid. Plus, now we're down here where we balance this 2Ki. So now we have 2K, 1+, that's aqueous. They're not really put together. And plus 2I, 1-, and that's aqueous. See, I wasn't kidding. That took the entire width of the page to write that. And this has a name. It's called the complete ionic reaction. That's this whole thing right there. The entire thing is the complete ionic reaction. Okay? Now, I'm going to combine this step 7 and step 8 because step 8 is going to ask us to cancel. And I don't feel like writing this equation all over again, okay? So what you're going to do is cancel anything that appears on both sides of the arrow. Why? Because it doesn't take part in the reaction. For example, the potassiums. You have 2 potassium ions that break off here, and they're still, by the end of the reaction over here, there's still 2 potassium ions. So since those ions don't do anything, they don't take part in the reaction, they just watch the reaction, they're called spectator ions, just like spectators at a football game. Okay? They're just watching. And so they cancel out, just kind of like we did with Hess's law. They cancel out. So you have one here, I'm going to just lightly put a line through it, and one here, that cancels out. All right? And then what else does that? Well, the 2 I's do that. The 2 iodides do that. So that cancels out with this 2 iodide over on this side. Okay, does anything else do that? Well, we have SO4. It only appears here. It doesn't appear anywhere else. We have Ca. It only appears here. It doesn't appear anywhere else. And then we have the compound of those two, which is CaSO4. That only appears here. It doesn't appear. So these are the ones that are left over. And those are the ones that are part of our reaction. The term net means you get rid of things and you just use what's left after you've gotten rid of the spectator ions. And so that's it right there. So I'm going to come over here and write something on the next page. It says eliminate ions. So we already did that back there. So I'm going to write this. What we had here. by not taking part in the reaction, what that means is they don't bond to anything in the product side. They're just still ions. They were ions at the beginning, they're ions at the end, so they don't take part in the reaction. They just kind of sit there and watch the reaction happen. Okay, and finally write the final net ionic equation. So that's what we had, what I put in the boxes there, so it would be this. So on the reactant side, these two separated from the other ions that they were with, but on this side they get put together again. And you always write cation first, the positive charge, the metal goes first. And you don't write the charges when it's put together because this is electrically neutral, the 2 plus 2 minus balance. In that compound, you do write the state, which is a solid. And that is your final net ionic equation, okay? A lot of steps. It is an AP level skill. You should know how to do this. And it's really not that hard if you practice a few more, and I'm going to give you a few more to practice, okay? Okay, so this video is right around 40 minutes, a little over, and that violates my 30-minute rule by quite a bit. So what I'm going to do is end this, and then you have 3 more of these problems to do. I'm going to do 2 of them here on the next video, and then the last one I'll totally leave for you, but I will give you the final net ionic equation so you'll know whether you did it right or not, okay? So we'll see you on the next video.